As we do our labs this semester, we will be looking at both quantitative and qualitative properties. Quantitative properties involve measurements with numbers. Those numbers also have to include a unit. 5 inches is much different from 5 miles, so the units are important. Qualitative properties do not involve measurements or numbers. We use our senses, such as sight, to make qualitative observations, such as color. For quantitative measurements, which make up most of what you'll be doing in the lab, units are important. The English measuring system is probably what you are most familiar with if you live in the United States. When you go to the grocery store, you buy a gallon of milk. When you go to the doctor's office, you find out how tall you are in feet and inches, and how much you weigh in pounds and ounces. The problem with the English system is that conversions are difficult and hard to remember. For example, memorizing that there are 1,760 yards in a mile is difficult. The metric system, on the other hand, has much easier conversions, all based on powers of 10. For example, there are 1,000 meters in a kilometer. Other common metric units include the liter and the kilogram. There are 7 official SI units. SI stands for Système International and is the official set of units that all scientists use. The unit for length is the meter, abbreviated M. The unit for mass is the kilogram, abbreviated kg. The unit of time is the second, abbreviated S. The unit of temperature is the Kelvin, abbreviated with a capital K. The unit of electric current is the ampere, abbreviated with a capital A. The unit of amount of substance is the mole, abbreviated by taking the E off and just writing MOL. And finally, the unit of luminous intensity is the candela, abbreviated CD. We will be using some of these SI units as what we call base units. For base units, we can use the meter, M, gram, G, second, S, liter, capital L, or mole, MOL. Notice that gram is our base unit, even though the official SI unit is the kilogram. Also notice the addition of liters to the list, which are not official SI units. To change the magnitude or size of our units, we will add prefixes. We can write out the whole word, such as picometers, or we could use an abbreviation, such as PM, in which the P stands for pico and the M stands for meters. The prefixes which make a unit the largest are at the top of this chart, and the prefixes which make a unit the smallest are at the bottom of this chart. Tera, capital T, giga, capital G, mega, capital M, and kilo, K, modify a base unit to become larger. Deci, D, centi, C, milli, M, micro, the Greek letter mu, nano, N, and pico, P, modify a base unit to become smaller. Many of the units are separated by 3 orders of magnitude, 3 powers of 10. For example, there are 3 orders of magnitude between milli, 10 to the minus 3, and micro, 10 to the minus 6. You will need to memorize this chart, especially everything from kilo on down, since we typically work with small things in chemistry. To convert between units, we will need to use conversion factors. To explain the concept of conversion factors, let's use some English units that you are probably already familiar with, and then we will move on to using metric units. We can use conversion factors anytime we have an equality that relates one unit on one side of the equation to a different unit on the other side of the equation. For example, we can use the equality that 1 foot equals 12 inches. We will turn these equalities into ratios with one of the units on top and the other on bottom. Each equality can be written as 2 different ratios, depending on which unit is on top and which is on bottom. For example, we can write 1 foot over 12 inches or 12 inches over 1 foot. When we multiply by one of these ratios, it is like in math class when you multiply by 1 over 1 and get the number you started with. Here we can get the result that we need because the top part of our ratio is equivalent to the bottom part of our ratio. To use conversion factors, we start by writing down the number we are given, then choose the conversion factor, or ratio, which allows us to cancel out the units we don't want and end up with the units we do want. Whatever unit we are trying to go away from goes on the bottom, and whatever unit we are trying to go toward goes on the top of our conversion factor. We also need to make sure the numbers in our conversion factor are in the right spots based on our equality. Once our conversion factor is set up properly, we can do the calculation. For example, to find how many inches are in 3 feet, we would start by writing out the number we know, 3 feet. Then we will choose a conversion factor that takes us from feet to inches. In order to cancel out the feet in our starting number, which are effectively in the numerator, we will need feet to be in the denominator of our conversion factor. Inches will go in the numerator of our conversion factor so that they will end up in our final answer. Typically, I will write the units in my conversion factor first, then I will fill in the numbers that go with them. In this case, 1 goes with feet and 12 goes with inches, based on our equality. By setting it up such that my units cancel out, and by filling in my numbers from my equality properly, I know that I need to multiply my original number of 3 by 12, and I come out with 36 inches. I can also convert in the other direction, from inches to feet. Again, I start out with the number I am given in the problem, 24 inches. Then I choose a conversion factor that takes me from inches to feet. In order to cancel out the inches in my starting number, I need to have inches on the bottom of my conversion factor. Since I am trying to solve for feet, feet need to go on the top of my conversion factor. I fill in my numbers from my equality, 1 next to foot and 12 next to inches. By making sure my units cancel out properly, and by filling in my numbers from my equality properly, I know that I need to divide by 12. 24 divided by 12 gives me 2 feet. Now that we have learned how to use conversion factors, let's apply them to some metric units. We can change orders of magnitude using equalities based on our table of metric prefixes. For consistency, I set up all of my equalities the same way. 1 times my prefixed unit equals my power of 10 times my base unit. The power of 10 that I choose is the one associated with that particular prefix in my table. To write the equality that relates milliliters and liters, I will write 1 times my prefixed unit of milliliters equals 10 to the minus 3 times my base unit of liters. I chose 10 to the minus 3 because that power of 10 corresponds to the prefix milli. Essentially, milli and 10 to the minus 3 can stand in for each other. They mean the same thing. My prefix and my power of 10 always go on opposite sides of my equality, and therefore opposite sides of my conversion factor. Again, I can write my conversion factor 2 different ways, either with milliliters on top and liters on bottom, or liters on top and milliliters on bottom. I will choose the one that allows my units to cancel out properly. For example, to go from 26.7 milliliters to liters, I would start by writing down the number I'm given, 26.7 milliliters. Then I would choose a conversion factor that has milliliters on the bottom to cancel out with the milliliters I start with. I would have liters on top, since that is the unit I am solving for. Then I fill in my conversion factor based on my equality. 1 goes next to milliliters, and 10 to the minus 3 goes next to liters. I always put 1 next to my prefix unit, in this case milliliters, and my power of 10 next to my base unit, in this case liters. Again, notice my power of 10 and my prefix are on opposite sides of my conversion factor. Once I have set up my calculation properly, I can do the math. 26.7 times 10 to the minus 3 gives me 0.0267 liters. Whenever I convert between two prefixed units, I use 2 conversion factors and go through the base unit. For example, to go from centimeters to kilometers, I would use one conversion factor to go from centimeters to meters, then a second conversion factor to go from meters to kilometers. I would need one equality for each conversion factor. The relationship between centimeters and meters is that 1 centimeter equals 10 to the minus 2 meters. The relationship between meters and kilometers is that 1 kilometer equals 10 to the third meters. Again, for consistency, I always write it as 1 times my prefixed unit equals my power of 10 times my base unit. If I want to convert 0.4 centimeters to kilometers, I start by writing down the number I'm given, 0.4 centimeters. Then I set up my first conversion factor with centimeters on the bottom to cancel out, and meters on the top, since that is the intermediate I'm going through. I fill in my conversion factor with the numbers from my equality, 1 next to centimeter and 10 to the minus 2 next to meter. I could get the result of this calculation and then do a second one, or I can string my conversion factors together. By stringing them together, I can avoid rounding error. Since my first conversion factor has meters in the numerator, I need meters in the denominator of my second conversion factor to cancel out. I need kilometers in the top of my second conversion factor, since that is what I am solving for. I fill in my second conversion factor with the numbers from my equality, 1 next to kilometer and 10 to the third next to meter. Once I double check that my units cancel out properly, and I've put the numbers from my equalities in the right places, I can do the math. I have 0.4 times 10 to the minus 2, then divided by 10 to the third. Instead of writing it as dividing by 10 to the third, I can write it instead as multiplying by 10 to the minus 3. So I have 0.4 times 10 to the minus 2 times 10 to the minus 3. When I multiply powers of 10, I add their exponents. So I get 0.4 times 10 to the minus 5. I express this in proper scientific notation by moving my decimal over one place to the right. And since I am making that part larger, I need to make my power of 10 smaller to compensate. My number becomes 4 times 10 to the minus 6 kilometers. In this poll question, you are converting between two prefixed units. How many nanometers are in 3.45 times 10 to the minus 1 micrometers? Is it A, 3.45 times 10 to the minus 4, B, 3.45 times 10 to the minus 10, C, 345, or D, 3.45 times 10 to the minus 7? In order to answer this question, we first start with the number we're given, 3.45 times 10 to the minus 1, and the units on that are micrometers. We're trying to solve for nanometers. In order to get from micrometers to nanometers, I like to go through the base unit, which is going to be meters in this case. So I'll set up my first conversion factor to go from my prefixed unit of micrometers to my base unit of meters. We could do this as a single conversion, or we can string our conversions together in a line. So I'm going to go ahead and write out my units for my second conversion, which is going to go from my base unit of meters, so I'll put meters on the bottom to cancel out, to my prefixed unit of nanometers. So micrometers will cancel out with micrometers, meters will cancel out with meters, and we'll be left with nanometers in the end, which is what we're trying to solve for. Once I've set up my units, I can add in my numbers. So I'm going to put in the relationships between my prefixed units and my base unit. So I always put a 1 next to my prefixed units and the power of 10 next to my base unit. The power of 10 that corresponds to micro is 10 to the minus 6. The power of 10 that corresponds to nano is 10 to the minus 9. That power of 10 needs to be on the opposite side of the conversion factor compared to the prefix because they mean the same thing. And we want the top to equal the bottom. So 10 to the minus 6 meters equals 1 micrometer. Once I've gotten it set up and I've made sure my units cancel out, micrometers canceling out with micrometers, meters canceling out with meters, then I can deal with the actual calculation. So I could plug it into my calculator as 3.45 times 10 to the minus 1 times 10 to the minus 6, and then divided by 10 to the minus 9. Remember, if the number is in the denominator, we divide, and if it's in the numerator, we multiply. Another way that I like to do it, so that I could do it in my head, is to put everything in the numerator when I can. So I could take this 10 to the minus 9 that's in the denominator and put it into the numerator by changing the sign on the power of 10. So I could change it from 10 to the minus 9 in the denominator to a 10 to the positive 9 in the numerator. So I could write out my string as 3.45 times 10 to the minus 1 times 10 to the minus 6. Since it's in the numerator, we multiply. And then times 10 to the positive 9. Once I get all my powers of 10 in the numerator, I can just add up the values of the powers of 10. So 9 minus 6 minus 1 equals 2. So I can write my answer as 3.45 times 10 to the 2. Now I look through my list of answers and I don't see 3.45 times 10 to the 2. However, I could put it into decimal form, and I see that the decimal form, 345, is one of the choices. So the correct answer is C, 345.